So yes, it's a great pleasure to welcome Professor Ruth Daly, who's coming to us from Penn State. Ruth is an expert in black hole systems and I would say in particular active galaxies, but it's more recently extended this into the study of vectoring binaries as well, I believe. Is that right, Ruth?
Yes, that's right. Mm-hmm.
So Ruth got her PhD originally from Boston University, and as many of you just heard, actually spent a few years at the IoA as a postdoc before moving then also for another postdoc at Princeton before ultimately joining the faculty at Penn State. And Ruth is going to tell us about black holes and things like black hole spin. So please take it away.
Thanks, Dom. So I'm going to be reporting on results that were published in the 4 papers listed here, in case anyone would like more detail. Let's see. All right. So there are 4 samples of sources I'm going to be focused on today. One sample of X-ray binaries. So these are stellar mass black holes with masses of around 10 solar masses. And they're in binary systems where they're accreting mass from a companion. And there's a powerful outflow shown here as a jet. All of the sources I'm going to be talking about have collimated powerful outflows. One sample I'll be studying and talking about are FR2 sources, classical double radio sources, and here's Cygnus A shown as an example in the upper left. And then I'll be talking about 2 samples of compact radio sources, illustrated in the bottom left, where the radio emission is coming from a compact area quite close to the AGN. So all of the sources, all of the samples have powerful collimated outflows, but they represent 4 different categories, 3 categories of AGN, and then the galactic black holes. The key parameters are the beam power of the outflow, which is the energy per unit time coming out in the form of a highly collimated jet, thought to be in the form of directed kinetic energy, the total radiant luminosity of the accretion disk, L bowl, and the black hole mass, which is capital M, or the Eddington luminosity. Now, you may be aware that there are many well-accepted methods to obtain the total radiant luminosity of the disk and the black hole mass, but there are very few methods to study and empirically determine the beam power. So I'm going to spend a little time on how the beam powers are determined, and then I'll show you the results by combining these 3 empirically determined quantities. So don't let this throw you. There's a lot on this screen, but this is how the beam powers are determined for the large classical double sources, FR2 sources. And this method can be applied to the most powerful of the FR2 sources. So it's not all FR2 sources, but they need to have an indication of a strong shock structure at the boundaries of the source. And in this case, the strong shock method can be applied, and I proposed it in 1994 and have worked on it for many, many years. Our most recent paper on it is O'Day et al. In 2009. And what happens is you basically use the property of the radio emitting plasma to determine the beam power using strong shock physics. And when you write down the equations of strong shock physics and look at how the empirically determined quantities enter, it turns out that the offsets from minimum energy conditions in this large extended region cancel out. So what that means is you get a really nice clean measure of the beam power independent of most assumptions, and the most important one that it's independent of is whether this is in equipartition conditions or not. Now, those beam powers form the basis of the use of FR2 sources for cosmological studies, which is another talk, but the key point here is that these have been used to determine coordinate distances, angular size distances, and luminosity distances for sources with redshifts between 0 and 2. And those distances and their first and second derivatives agree with the ones obtained with type 1a supernovae over the same redshift interval. So this is another indication that these beam powers are reliable. For the FR2 sources, the AGN is sitting down here at the very heart of the radio image I'm showing, and the radio emission is very extended. So to get the bolometric luminosity of the accretion disk, for the studies I'm going to be showing you, the oxygen 3 luminosity was used, and a standard conversion that has been investigated by many groups and is rather well accepted. Black hole masses are from McClure et al., again, with relatively well-known, well-accepted methods. Combining all these led to a sample of 97 FR2 sources with redshifts between 0 and 2. These are the quick results from the 2016 paper applying that. So looking at the empirically determined beam power relative to the bolometric luminosity of the disk versus the bolometric luminosity of the disk in Eddington units, okay? So now we want to add a significant, additional samples. And you probably have heard of the fundamental plane of black hole activity. The fundamental plane of black hole activity can be applied to sources with compact radio emission. So now the radio emission is coming from a region quite close to the black hole, and it's a compact radio source. So it's not an FR2, it's not an FR1, it's a compact radio source. And the fundamental plane was originally found not including the black hole mass for galactic black holes, stellar mass black holes that are parts of X-ray binaries. But then it was expanded to AGN in 2003 by Merloni et al. In 2004 by Falke et al. By including the black hole mass. So this is a relationship between the radioluminosity of the compact radio source, the X-ray luminosity of the accretion disk, and the black hole mass. And the really interesting result is that this relationship holds over an enormous range of mass, about 9 orders of magnitude when you include the range of mass for AGN plus going down to 10 solar masses for galactic black holes, stellar mass black holes. So having obtained this relationship for the FR2s, it seemed like which is basically shown by equation 2, it wasn't much of a stretch to realize that the fundamental plane is possibly the empirical manifestation of a relationship like equation 2. And in fact, in the studies that many authors have published papers on, there's standard relationships that are adopted between the bolometric luminosity of the disk and the 2 to 10 keV X-ray luminosity of the source. This would be coronal X-ray emission. And you can get the bolometric luminosity by multiplying that by a constant. Of course, the Eddington luminosity is simply related to the black hole mass. And there's a power law relationship between the beam power and the radioluminosity. And in the original studies, detailed jet models where you have a particular Lorentz factor for the outflow, particular opening angle, et cetera, a lot of parameters describing the source, you could get very reasonable agreement between this kind of relationship and the fundamental plane. So what I did with a couple of undergraduate students in 2018 was to ask, well, if we map equation 1 into equation 2, what do we get for the beam power? So taking these 3 relationships down here and substituting in, so eliminating the radioluminosity using this equation, eliminating the black hole mass using this equation, eliminating the X-ray luminosity using this equation, and rearranging and asking when can equation 1 be written in the form of equation 2? Well, it occurs when this value C, the coefficient here for the beam power, goes as 1 over A plus B, these 2 coefficients in the fundamental plane relationship. And when the constant capital D is this particular combination of constants. So if C and D can be determined, which they can here, you can actually use this to solve directly for the beam power, okay? So now you'll notice the expression for capital D includes this value capital B here. So in using this method to obtain beam powers for the fundamental plane sources, the value of B obtained in my 26 paper has been adopted, okay? So basically, rather than picking a detailed model to go from the radioluminosity of the compact radio source to the beam power, a model that depends on the Lorentz factor of the outflow and multiple other factors, we use this mapping, okay, to determine the beam power. And that way it's determined completely empirically, and it does not depend on a detailed model for the outflow. So now applying that to the 3 fundamental plane samples. So I have still the FR2s that I showed you obtained, as I explained, shown here in black. These black circles are the FR2s. And now there were 576 liners that lie on the fundamental plane from Nisbet and Best. And using those methods I just described to get the beam power, the bolometric luminosity and the Eddington luminosity, those are shown here in green. Interestingly, they come in with a slope that is quite similar and consistent with that obtained for the FR2s. There are 80 samples in the original Merloni, 80 AGN in the original Merloni et al. Sample, which are all quite local AGN, which is really nice because you had a very large range of luminosities in bolometric luminosities relative to the Eddington luminosity, and even just in terms of the bolometric luminosity. So that's another sample of AGN. And then 102 measurements of 4 galactic black hole systems, 10 solar mass type X-ray binary systems, with a black hole as a mass of around 10 solar masses. And those systems are highly variable, but the radio and X-ray emission vary in sync. And so there were 4 systems with 102 simultaneous X-ray and radio observations. Later on, I'll show you the results for each of the 4 individual galactic black hole systems. So the interesting result we found in 2018 is that these slopes are all consistent, and very similar results are obtained with the different methods to obtain the beam power for the FR2s and the 3 fundamental plane sources. And this represents 4 different categories of black hole systems: the FR2s, the liners, the local compact radio sources, which are Seyferts and liners, and the galactic black hole systems. And so we see this enormous range of LJ over L bol of the beam power relative to the disk bolometric luminosity, about 4 orders of magnitudes or so, and then also a very large range in bolometric luminosity in Eddington units. Interestingly, this does cut off at a bolometric luminosity approximately equal to the Eddington luminosity, and that's a result. That's not something that was imposed. And so I've taken this to mean that these sources are all governed by the same physics. They all have a very similar slope, same normalization, which has many factors, including the normalization from the FR2s, but it also has several other factors. And it can be described by this equation shown in the lower right. And this is a strictly empirical relationship. So there's no accretion disk model, there's no detailed model to obtain the beam power. That's all empirically determined. And then it's easy to flip this around and plot it, the beam power in Eddington units versus the bolometric luminosity in Eddington units. And later on, when I go to normalize the bolometric luminosity we will have a factor, a normalization factor of 1, because that the maximum possible bolometric luminosity seems to be coming in quite naturally at about 1. On the other hand, the beam powers are cutting off here at about 10 to the minus 1. So later on, when I take a normalization for the maximum beam power in Eddington units, I'll be taking a value of 0.1. So those results are for, well, I'll get to that in a little bit. All right, so now that we have those empirical results, what about the theory? Well, I have argued that based on this figure here, where we have sources with beam powers that are 10 to 100 times larger than the radiant luminosity of the disk, those sources are probably spin-powered outflows, as many people have suggested for a long, long time. The liners and the Seiferts here are probably spin-powered. And you can see it would be very difficult to get a beam power that large relative to the radiant luminosity without a spin-powered outflow. Now, everything else is lining up with a similar slope and normalization, so that would suggest that these are all spin-powered outflows. So now let's go to the theory on spin-powered outflows. Just a few notation comments. I'm using the symbol little j for the dimensionless black hole spin. Sometimes it's denoted by a symbol A star or capital or lowercase a. So this is all the same quantity. The spin function f of j is used to describe a spin-powered outflow, and it's proportional to j squared to first order. We can write it as capital F squared, where capital F is given by this relationship, but to first order in j is proportional to j, okay? And later on, you'll see capital, well, I'll get to that later on. All right, so now we have a spin-powered outflow, for example, in the Blanford-Zinyayak mechanism, where the outflow is powered totally by black hole spin, or in the Meyer model, where there are where the outflow is powered by both black hole spin and a wind from the accretion disk. And in a lot of the numerical work, this is the main representation for the beam power relative to the properties of the black hole and the accretion disk. So the function f of j describes the input from the spin function to the beam power. The black hole mass enters as black hole mass squared, and this is the poloidal component of the magnetic field that is anchored in the disk and is threading the black hole. Now, when I was doing these studies, I was asking myself, can I rearrange this to write it in a functional form that looks like the empirically determined functional form? And the answer is yes. And you can do that by taking 1 power of the mass over to the left-hand side and writing that as Lj over L Eddington, and using this representation discussed by Martin Rees in 1984 and discussed frequently at around that time, is that you can define something called the Eddington magnetic field strength, B sub ed, and it has a pressure similar to the pressure of a radiation field with the Eddington luminosity. And it scales, B ed squared scales as mass to the -1 power, the black hole mass to the -1 power. So 1 power of the black hole mass comes down here. And so this allows us to rewrite the theoretical equation for these sources in dimensionless separable form. Now, the poloidal component of the magnetic field in units of the magnetic field strength is absorbed into the coefficient G sub j, the normalization factor of the beam power. And the reason I did that is that I wanted to have this term here, B over B ed squared, that applied to the full accretion disk properties, not one particular component of the magnetic field. So that's why that is absorbed into G sub j. Now we can compare the empirically determined relationship, which has this form, Lj over Led goes as L bull over Led to the power A. A is empirically determined, as I showed you earlier. And everything in this equation is empirically determined. So there are no models in that. Now we can compare that with our theoretically predicted relationship, and basically we can identify the term that applies to the full accretion disk in the theoretical relationship and the full accretion disk in the empirically determined relationship. All right, so it's identifying terms. Now, originally in the 2016 paper and in the 2019 paper, you can also derive this in other ways. But this is the simplest, easiest way to see it. So identifying terms, we see that B over B ed squared equals L bull over L ed squared, L ed to the power A, where I've taken the normalization factor for the bolometric luminosity of the disk to be 1, as indicated empirically for the sources under study here. And when I do need to take a value for G sub j, which is normalized also in terms of the Eddington luminosity, a value of 0.1 is adopted here. But I always keep in mind that does have the term B poloidal over B squared in it, and that could vary from sample to sample. But in the first results of this new method that are described in my 2019 paper, one value is adopted for all the different samples studied. All right, so now we have this identification and we're able to get B over B ed squared empirically using L bull over L ed to the power A, where A is a little different for each sample studied. And in all the work I'll be showing you, the value appropriate for each sample is used. Then you can use this to solve for the magnetic field strength. So this would be the full magnetic field strength of the field that's anchored in the accretion disk, okay? So first I'll show you the results for the magnetic field strengths, and then I'll go on and show you the results for the black hole spin. So now that we have this relationship, we can substitute that back into our theoretical equation and solve for the black hole spin empirically, okay? So this is the expression for the black hole spin function. So this was in my 2016 paper and the 2019 paper. And as I mentioned, G sub B will be taken to be 1, the normalization factor for the bolometric luminosity in Eddington units, and G sub J will be taken to be 0.1. When I do show you the results for the spin, the square root of the spin function, capital F, which goes as J to first power in first order in J, when I convert capital F, which is what is obtained empirically, to J, J is constrained to be less than or equal to 1 because of this term 1 minus J squared. So any value of F greater than 1, determined to be greater than 1 empirically, will be mapped to a spin of 1. All right, so now here are the 4 samples. So in all of the figures, the 576 liners will be shown in green. The 80 Merloni et al. Sources will be shown in red. The 100, I added 3 more from 2016, so we went from 97 to 100 FR2s will be shown in black. And 102 measurements of 4 galactic black hole systems are shown in blue. So this is what is obtained. On the left, the magnetic field strength in Eddington units, how it's obtained empirically is shown here, L bull over L ed to A divided by 2. A is somewhere around 0.4 to 0.5 for the different samples. This is approximately the power 0.3, say, or 0.2. All right, so we see here that the magnetic field strength in Eddington units for these accretion disks does vary by AGN type, and that is expected and had already been reported by Ho, that basically AGN type is related to the quantity L bull over L ed. Now, when we multiply this by B sub n to recover the magnetic field strength, we have this very interesting result that the AGN are lining up here at around 10 to the 4 Gauss, and the stellar mass black holes are lining up at around 10 to the 8 Gauss. And those are the types of field strengths that are obtained independently for the galactic black hole systems, where detailed models are adopted for those systems, and in the context of those models, magnetic field strengths are obtained. And similarly for the AGN, field strengths of around 10 to the 4 Gauss for AGN accretion disks is a typical number. Now, you can sort of see here that there's a hint that the Merloni et al. Sample might be splitting into 2 samples. And in fact, when we look at the efficiency factors for the bolometric luminosity of the accretion disks, we'll see that in fact the Merloni et al. Sample does split into 2 subsamples. Now, in looking at these histograms, I found it's very helpful to look at the quantity as a function of redshift, so you can sort of see by eye the selection effects that might be entering due to flux limits for samples of sources being studied. Now, the galactic black holes are not included on the redshift distribution here, and this is going out to a redshift of 2. So we see here that the Merloni et al. Sample is a very local sample and has a very broad range of magnetic field strengths. And here we have the Nisbet and Best sample shown in green, and the FR2s shown with the black symbols. If you're interested, the stars are quasars, the open symbols are high excitation radio galaxies, and the squares are low excitation radio galaxies. But what we see here on the right is that there's really no strong evolution of the magnetic field strength of the disk with redshift, and we see a pretty symmetric distribution here. And that's why these histograms are relatively symmetric for the magnetic field strength. So the way the empirically determined quantities are entering, we are not seeing strong effects due to the flux limited nature of the surveys being used. All right, now before I show you the results for the spins, this is just to remind you where we are. We have 576 liners. The overall spin function, square root of the spin function, which I call capital F, is coming in with a spin function centered at about 1. And with a broad range on each side. So indicating rapidly spinning black holes. This is the mean value for the full 576 sources. The 0.24 here is the dispersion of the spin functions for those. And then the numbers in brackets is the estimated uncertainty per source. Okay, so pretty similar values for the liners and the FR2 sources, and then the compact radio sources by Merloni et al. And the X-ray binaries come in with a lower value of capital F, which is almost certainly due to the fact that the FR2s and the liners are very strongly affected by the flux limited nature of the surveys used to study them, whereas the Merloni et al. Sample is quite local and goes much deeper into the luminosity function, and the X-ray binaries are right here in our galaxy. So in mapping from capital F to the spin J, this pulls down J a little bit for the full distribution because the sources that had capital F greater than 1 got mapped to a spin J of 1. And the dispersion here is the dispersion of the population. Now, down here are some sources, are the results for the 4 individual stellar mass black hole systems. So GX339-4 had 76 simultaneous radio and X-ray observations. So the black hole mass is fixed, and as the accretion rate changes, the bolometric luminosity of the disk changes, and the beam power changes. So you want to have simultaneous measurements so that you're comparing the beam power and the radio power, or bolometric luminosity and beam power, at the same instant. And you can see that the spin obtained with this method, which I call the outflow method, obtained for with these 76 measurements, comes in at around 0.92 plus or minus 0.06. Now that can be compared with the independently determined spin obtained with the X-ray reflection method, which comes in at around 0.94 or 0.95. Now, almost all of the values obtained for capital F for this source are less than 1. So we don't have an effect here of having an impact of having sources with F greater than 1 being mapped to spin of 1. The value here is the dispersion of the spin for these 76 sources. Okay, and the uncertainty per source would be per measurement per source is around 0.07. Now you can also notice that the dispersion of the magnetic field strength in Eddington units, which I will show later is related to the dimensionless mass accretion rate, is about 3 times larger than the dispersion in the spin. And I'll show you later on a figure, you can see quite easily the enormous dispersion of the accretion rate, or the properties of the disk, relative to the spin. And that's because as the accretion rate is changing, the magnetic field strength in Eddington or physical units are changing, but the outflow, the beam power, is adjusting in sync with that, so that when you use those combined together to solve for the spin, you're getting a smaller dispersion. All right, so here are some sources of interest. Here are the 3 other galactic black hole systems and the spin values obtained. I included Sagittarius A star and M87 here. And then there are 6 AGN with X-ray K alpha iron line, or X-ray reflection determined spins. And there's reasonable agreement between the spins obtained with this method and those obtained with the X-ray reflection method. These uncertainties are quite large, and we now have a new project underway where we're going to be able to compare these in much, much greater detail with simultaneously obtained X-ray and radio measurements. So over here, the spin values obtained with the outflow method for the AGN do not have simultaneous or even contemporaneous radio and X-ray observations. So the variability of the AGN could be a factor. But very shortly, we're going to have a substantial number of sources where we will have simultaneous or contemporaneous radio and X-ray measurements for a large sample of local AGN, and we'll be able to compare the spins obtained with this method to higher accuracy than we're able to do at this. This is really the first look of the application of this method. So here are the spins, and here are the uncertainties up here. So in all the figures, I show the square root of f of j over f max, which goes as the spin or spin function capital F. And here's Sagittarius A star in case anyone is interested. And here is our line where the spin would be 1, or F would be 1, and everything up here sort of has a spin larger than expected. And everything down here would have mapped to a spin of 1 or less. Now the uncertainties on this are shown up here in this order. So for example, for the Maloney et al. Sample, propagating through the empirical uncertainties of all the quantities that go into capital F, which is the square root of f of j over f max, are around 0.2. So just the 1 sigma uncertainty for those sources is coming up here at a rather significant value. So we're going to be working on getting those uncertainties low, decreasing those empirically determined uncertainties. For the FR2s and the liners, that value is around 0.15, 0.15 to 0.2, similar kinds of numbers. Now, when we take this and map it over to black hole spin, as I mentioned, everything up here gets collapsed down to a spin of 1, and then these are the sources with spins less than 1. And once again, you can see this lining up in terms of the magnetic field strength in physical units. You can see the broad range of spins for the Maloney et al. Sample. Again, that's because that sample does not have a flux limited selection effect. So you can see much deeper into the luminosity function and see much lower black hole spins. Now, when we look at these spins as a function of redshift, there is a very strong selection effect. And we can see that here in the histogram. We're really missing the low spin objects for the Nisbet and Best sample, 576 liners, and also for the FR2 sources. All right, so you can see here that there's a very strong flux limit that's impacting this, and we're missing these low spin objects. Now, the Nisbet and Best sample comes from the first radio survey, an XMM X-ray survey, and SDSS results to get black hole masses. And so if the flux limited nature of any one of those surveys, if you're missing a source from any one of those surveys, it's not in this sample. And you can see that quite clearly here. So that's why we're missing these low spin objects for that sample. And there's a similar effect for the FR2 sources, where we're missing the low spin objects. And then when we map to a spin of 1, a spin J, where anything that had a value of F greater than 1 gets mapped to a spin of 1, now you can really see that flux limit coming in here quite strongly, where we have a very broad range of spins for the local Maloney et al. Sample and the very strong cut, and we're missing all these low spin objects, even at a redshift that's 0.2 to 0.3 for the liners, where the Nisbet and Best sample was by hand cut off at a redshift of 0.3. All right, so when we look at the spins, we can see this broad range from around 0.3 or so up to 1 for the Maloney et al. Sample, and then we're missing lower spin objects for the liners and the FR2s. Now, for those of you interested in stellar mass X-ray binaries, this is showing the spin function, capital F, or the square root of F of J over F max, versus the Eddington field strength. The field strength in Eddington units, which we'll learn soon, is also the dimensionless mass accretion rate. And you can see, for example, 76 simultaneous radio and X-ray measurements of GX339-4 are shown here as circles. And well, first you can see that all of these spin functions are pretty much staying below the F = 1 line. There's a very broad dispersion in the properties of the accretion disk, but there's a very small dispersion in the spin function. And what that means is that as the properties of the disk are changing, as the mass accretion rate and other properties of the disk are changing, the outflow is also changing. The beam power is changing in sync with that. So when you combine them empirically to solve for the black hole spin, you're getting a small dispersion in the black hole spin. And that's exactly what you would expect in the outflow method. And I'm working on a separate paper now where I calculate the change in the black hole spin due to the energy extracted during these outflows. And that is a small fraction. So for the outflows that we're looking at here, the fraction of the spin energy extracted over the time scale of the outflows is very small. So we expect these spins to remain roughly constant. And you can see the different values for the different stellar mass black holes. They all have roughly a mass of around 10 solar masses. So the crosses are V404 sig A, and a lot of them cluster around here, and there's one measurement here. There are 5 measurements of J118 plus 480, and they're all very, very similar. They're all sort of lying on top of each other here. And then in this figure, I show one measurement of A06200, but Chris Reynolds, thank you, Chris, brought to my attention a 1975 measurement of that where there was an X-ray outburst, and I found simultaneous or contemporaneous radio information, and in the 2019 paper, calculate the second point of this source with that information from 1975. And in fact, the spin comes in almost exactly the same, but the mass accretion rate is putting it over in this cluster. The value of B squared over B ed squared is putting it over with this other cluster of data points. So it might be that these 2 points, one for A06200 shown here and one for V404 sig A, is sort of an entry or exit point when the accretion disk is still radiating the radio and the X-ray required, which is required to get these data points, and is either just turning on or just turning off, might be one possibility. All right, now to study mass accretion rates in physical and dimensionless units, the beam power, I suppose I'm hypothesizing, although it's probably published by someone else in some other paper, that this goes as m dot f squared. So we expect for a spin powered outflow, we're going to have in our equation for the beam power capital F squared. And for dimensional arguments, you'd say, well, it's going to be dm dt, because we're going to want erg per second here. So it's dm dt f squared. And then defining the dimensionless mass accretion rate in terms of the physical one and the black hole mass, we obtain this equation for the beam power and its relationship to the mass accretion rate dm dt. Now, in the definition I use for the dimensionless mass accretion rate, I do not include the bolometric, the efficiency factor for the bolometric luminosity of the disk. I keep that separate and study it as a separate parameter because in my 2016 paper, I'd already showed that for these sources, epsilon bol cannot be constant. So you can see right away from the empirically determined relationships, this has to be a variable. And so I left it explicitly as a parameter to be studied. So now comparing our spin-powered theoretical equation written in our dimensionless separable form, which I explained earlier, we can identify the dimensionless mass accretion rate with B over B ed squared. And so we can then determine that empirically using this relationship. It goes as L bol over L ed to the A. A is the slope of the empirically determined relationship I showed you earlier. It's around 0.45 for most of the samples. But the value for each sample is used for the results I'll show you. And then you can just unwrap this, multiply, remove the definition that we put in earlier and solve for this in physical units. And then we can also get the efficiency factor for the radiant luminosity of the disk, and that turns out to be equal to L bol over L ed to the 1 minus A, so around the power 0.55. And then you'll see that the efficiency factor, the radiant efficiency factor of the disk, can also be related to the dimensionless mass accretion rate. Now, in all of this, there's no specific accretion disk model adopted. Everything here is empirically determined with this relationship is adopted. So this, I suppose you would take as an assumption about the accretion disk, although it's not it's not adopting a particular specification for the accretion disk model. Now, I'll also show you what I call the spin to disk efficiency factor. It's basically asking how much of the beam power is coming from the spin of the black hole relative to the dimensionless mass accretion rate. So how much of the dimensionless beam power is being powered by the spin versus being powered by spin energy, the mass accretion rate of the disk. So that's shown here. And interestingly, when you write that down in terms of empirically determined quantities, it ends up being about Lj over L bol. Okay, there's another term here that's extremely weak, L bol over L ed to the 0.1. So this sort of goes along with your intuitive sense that Lj over L bol gives you an estimate of the relative impact of spin and the properties of the accretion disk on the outflow. I'm calling it this efficiency factor, the spin to disk efficiency factor. But basically it's saying that the ratio of Lj over L bol is providing a measure of the importance of spin relative to accretion for these sources. Okay, so here are the efficiency factors for the bolometric luminosity of the disk. And you can see that the liners come in with a relatively low value, all right, ranging from about 10 to the minus 1.5 to about 10 to the minus 3.5. The FR2 sources and the galactic black holes, the stellar mass galactic black holes, are coming with a high efficiency factor. And the Maloney et al. Sample splits into two subsamples, which is sort of probably related to the little offset we saw in the magnetic field strengths. So you can see that there's a split here at an efficiency factor of about minus 1.5 for the log of L bol efficiency factor of the bolometric luminosity. And there's this group over here of sources which have a high value, and then a dearth of sources, and then these sources over here with a low value. And also we can see that we're missing the low epsilon bol sources due to the flux limited nature of the survey. Okay, sorry. So anyway, this distribution for the liners is probably cutting off at low L bol due to the flux limited nature of the surveys used for that. You can see here quite nicely the very sharp cutoff at epsilon bol equal to 1, which is showing you in another way that the bolometric luminosities of these disks are cutting off at the Eddington luminosities. The uncertainties of the quantity per source are shown up here. So significant uncertainties in the quantity L sub bol per each observation. Now, there are some independent results for these efficiency factors and for the mass accretion rates I'll be showing you in just a moment. And in Raimondo et al. In 2012, efficiency factors for the radiant luminosity of the disk were obtained for many, many sources. And I selected the sources that overlap with the sources that are in the samples that I'm working with. So this is showing their value, the value of epsilon bol obtained using one method by Raimondo et al. Then they had a second method which they applied to 2 of the same sources. This is the value that I obtained for the efficiency factor, radiant efficiency factor of the disk, and this is the ratio. So the ratio shows that for most of the sources, these are agreeing to factors of 3, 2, or 3, which seems to be similar to the internal consistency of the factors obtained by Raimondo et al. With independent methods. So we also should keep in mind that the Raimondo et al. Results are done just looking at the accretion disk properties. So they don't include anything about the outflow, whereas the work that I'm presenting has to do with looking at the functional form that includes the outflow and the disk. So if the observations I'm using are not obtained simultaneously, that could impact this efficiency factor. In any case, here are the ratios shown for these values. So they're coming in, accurate to, consistent to a factor of 2 or so, and in fact, about a factor of, except for one source, which comes in off by about a factor of 10, and we'll see that also in the mass accretion rates. So while I'm here, I'll mention the mass accretion rates. Zhang et al. Had mass accretion rates in dimensionless units for 8 sources that overlap with the sources that I studied. Here are the mass accretion rates I obtained, and here are the ratio of those dimensionless mass accretion rates. So they're consistent to a factor of 2 or so. Now here, Raimondo et al. Reported those mass accretion rates in physical units. And so the rates in physical units can be compared to the rates I obtain in physical units. And the ratio comes in, again, consistent to factors of 2 or 3, except for 2 sources that are off by a factor of about 10, one of which also is off in the efficiency factor. And as I mentioned, we're now exploring this effect of time variability of the accretion disk properties on the results with a large sample of sources. Now there's one source here where it's common to both samples. Markarian 279 comes in at a ratio of about 1 here and a ratio of about 0.64 here. And that might be, if the Zhang et al. Result for little m dot, the dimensionless mass accretion rate, had absorbed the bolometric efficiency factor into their definition, then that might account for this difference. I like to compare the physical mass accretion rate, because the physical mass accretion rate should be the same even if it's derived assuming a different relationship between dimensionless m dot and capital M dot. Sometimes in the definition of the dimensionless mass accretion rate, the efficiency factor is absorbed and put down here with the black hole mass. So that might affect this comparison, but I didn't find it discussed in the paper, so I'm not sure. But anyway, in any case, that might account for this slight change and would indicate that this difference is pretty small within the noise of these comparisons. All right. So so here is the dimensionless mass accretion rate. It shows a similar, it's not quite as pronounced as the separation of the Merloniol sample into 2 components that we saw for epsilon symbol, but we can still see that there's an overlap of a part of the Merloniol sample with the FR2 sources in the galactic black holes, sort of bright accretion disk type systems. And then with the less radiatively efficient systems, there's an overlap of some of the Merloniol sources with the liners. And once again, we see the strong effect of the flux limited nature of the surveys for the liners. In terms of physical mass accretion rates, we don't see the Merloniol sample split into 2. Looks like a pretty smooth curve here. Here's Sagittarius A star down here coming in at around 10 to the -6 or so for that one snapshot in time of Sagittarius A star. The dimensionless mass accretion, the physical mass accretion rate as a function of redshift has an enormous impact due to the flux limited nature of the surveys, and we can see quite clearly that we're missing the low capital M dot systems at high redshift. Comparing these with values of the mass accretion rate obtained in the context of a specific accretion disk model, the galactic black holes, actually come in right between 10 to the minus 8 and 10 to the minus 9 or so solar masses per year, right in the middle of the values that people obtain with very, very detailed mass transfer and accretion disk models for those systems. Similarly, I showed you for the overlap with the Raimondo et al. And Zhang et al. Sources. We're getting nice agreement with capital M dot, and all of the overlap sources are drawn from the Merloni et al. Sample. All right, so here is the spin to disk ratio, that efficiency factor, which is F squared, the input to Lj over Led from the black hole spin divided by the mass accretion rate in dimensionless units. And we can see that some of the sources are completely dominated by the black hole spin. And that's been thought for a long, long time for the liners, where the radioluminosity is really significant compared to the X-ray luminosity of the source. Interestingly, this lines up, as I showed earlier, this efficiency factor that measures the impact of the spin on Lj to the mass accretion rate is really reflected in Lj over L bowl. So if we look at this and go back to our original figure of Lj over L bowl versus the radiant luminosity of the disk in Eddington units, this cut is coming in at around 10 here, I guess I would say, where you have a lot of sources that are radiatively efficient, which have small values of Lj over L bowl, and then these other sources that have large values of Lj over L bowl. Because this has this Gj to the minus 1 in it, which is about a factor of 10, this is shifting this by about a factor of 10 from this figure here. Okay, so that's putting the cut here at about 10 to the minus 1 for Lj over L bowl. So just to remind you, Lj over L bowl greater than 1 would be considered a jet-dominated system. And Lj over L bowl less than about 1 would be considered a disk-dominated system. And what this is showing is that this ratio, Lj over L bowl, actually is measuring the relative impact of, what's happening? The relative impact of the input from the spin divided by the dimensionless mass accretion rate. This, I seem to be stuck. Let's see. Well, I guess I'll go to my summary slide. Oh, right. Okay, so here are the key results obtained with the outflow method. There are 3 empirical indications that the outflows are powered by black hole spin for the sources studied in the as explained. There are many sources with beam powers 10 to 100 times larger than the radiant luminosity of the disk. And it's hard to understand how such a powerful outflow could be produced unless it's spin powered, as has been pointed out by many people for a long time, especially with regard to liners. The second is that the accretion disk magnetic field strengths obtained in the outflow method, which relies on the functional form of a spin-powered outflow, those field strengths agree with those obtained in the context of specific accretion disk models that do not consider the outflow at all. So that's suggesting that the outflow method is on the right path, and this is a very encouraging result. In addition, the mass accretion rates and efficiency factors obtained with the outflow method agree with those obtained by applying a specific accretion disk model, which as was done by Raimondo et al. And Zhang et al., where there's no input at all that's related to the outflow properties. So the fact that these agree suggests that the values obtained with the outflow method are reliable. The second key result is that the black hole spins obtained are unrelated to source type. So for all 4 categories of black hole systems studied, including the galactic black holes, the stellar mass black holes, the liners, the local AGN, including Seyfert type and liner type systems, and the classical double sources, including the high excitation, low excitation, and radiolog quasars, black hole spin is not related to type for any of those sources. The next big result is that the spins are relatively high. So even including many nearby low luminosity AGN, the spins range from about 0.4, 0.5, 0.6 to about 1. And for the non-local samples, the preponderance of the high value spins is probably due to selection effects. The method and the results are all empirically based. They're independent of any specific accretion disk model and any independent of a specific jet model relating in detail the beam power to the radio emission. So that means that these results can now be applied to study and constrain accretion disk models and detailed models of jet formation. Thank you.
Thanks so much, Ruth. I will just quickly stop the recording and we can hopefully still squeeze in a couple of questions for you.